So following the same process that we did in class on Friday, we're going to take this. Our goal is to find all the zeros and eventually factor it. When I look at this, I see it's a fourth degree polynomial, which means that I should have 4 zeros, although I know that some of them could end up being repeated. But I know I could have as many as 4. That also means that I should be able to, at the end of the day, factor this thing into 4 factors. I'm on freeze, my bad. Here. So I should be able to come up with 4 zeros, and I should be able to eventually rewrite my function as the product of 4 factors. Now, again, some of these factors might be repeated, so we might end up writing it as a factor squared rather than having 4 factors. We might have 3 factors, except one of them squared, something like that. But we're going to assume right now that we have 4 factors. 4 zeros, 4 factors. So we're going to use our calculators to get some hints because we know zeros correspond with x-intercepts. So we're going to graph this thing on our graphing calculator. We're going to look for x-intercepts and hope that we see some x-intercepts that are nice and easy to see. So when I graph mine, it looked like this. And I can't really see exactly what's going on here because it goes way up above the top of my screen, but I can see my x-intercepts. So that's kind of the key thing. So it looks like I've got one exactly at 2. Looks like I've got one really close to 0, but not quite hitting 0. A little bit negative, a little bit to the left of 0. Somewhere between 1 and 2, and then another one between 3 and 4, closer to 3 than to 4 definitely. The -2 is promising to me. It looks like it's crossing right at -2. So do you remember how we checked to make sure that that's actually a 0? We can plug it in with synthetic division, or we can just let our calculator do the work for us. Our calculator will evaluate the function at any x value. You just go to second calc value, give it the value you want for x. I think it's crossing at -2. Hit enter. It'll plug -2 into your function and tell you what the y value is. If it comes out to be 0, then that is indeed a 0, and it is. I got y equals 0. So I know from my calculator and from the graph that -2 is a 0, which means that x plus 2 is going to be a factor. All right, so these both came from the calculator, from the graph. All right, now let's focus on the other ones that are kind of in between. I want to focus on this one right here. I know that there's one between 0 and -1. So it's this point that I want to be looking at my P over Q list. So let's go ahead and generate our P list and our Q list for this particular polynomial. And that'll help us find any fractions that we can make to create rational zeros. So my P lists are going to be factors of 30. There's quite a few of them, unfortunately. 10, I almost drew 12, but 12 doesn't work. 15 does. And 30. Is that it? Did I miss something there? 2, 4 don't work. 7, 8, 9 don't work. Yeah, that's it. And then Q would be factors of 12. So my P list is factors of 30. That's my constant term. My Q list is factors of my lead coefficient, which is 12. So 1 goes into 12, as does 2 and 3. 4 goes into 12. 5 doesn't. 6 does. 7, 8, 9, 10, no. 11, no. 12, yes. And that's a bunch. So one of our zeros is definitely between 0 and -1. So let's think of all the fractions that we can make between -1 and 0. This is the interval from -1 to 0. Out of these, remember, P's got to go on the top, Q's got to go on the bottom. So I'd say -1/2, we can make that. That's between -1 and 0, right? Or -1/3, or -1/4, or -1/6. Oh man, there's a lot. Or -1/12, or what else? 2/3, -2/3, -2/4, but I've already got that, right? That's the same as -1/2. Sorry, you said 3. Oh, 3/4, -3/4, -5/6, -5/12. And I think that's it. That's a big list. So we're gonna go through, we're gonna try those all in our calculator. Now, we can be kind of smart about some of these. If we look at our graph, that looks like it's really close to 0, isn't it? So I think like -5/6 is probably going to be too big. But we can try these. It wouldn't take too long. Just second calc value, -1/2. Enter. Does that give us a y of 0? Nope. Then keep going. Oh, here's a little shortcut for you. If you just did second calc, you can just go ahead and type another number in. You don't have to go back and do it again. So after you hit enter, for your first x value, you can just type another x value in and hit enter, and it will do it again. So I just did -1/3. That did not give me 0. We'll try -1/4. Nope. -1/6. Nope. -1/12. No. -2/3. No. Man, unlucky. -3/4. No. -5/6. No. -5/12. No. Okay. So we exhausted the whole list and it didn't work. And that was kind of tedious, but imagine if you had to do that by hand with synthetic division, right? So at least we get to use the calculator for it. Are you okay with how we're using the calculator to check those? Are you guys okay with how we generated that list? Okay, we generated from this, and we're looking for specifically for things between -1 and 0. So basically, I know that what about this 0 right here? There is a 0 here, but it must be irrational. It's not on our list, so it must be irrational. All right, so that ain't gonna work. That is not going to work. Better. There's another 0 between 1 and 2, so let's do the same thing. Hopefully we don't have as many to check this time. Make me some fractions between 1 and 2. What could you come up with between 1 and 2? Not including, because I can tell it's definitely in between, right? So that's why I put parentheses around the 1 and the 2. So what's the first one you can come up with that would end up between 1 and 2? 3/2. That's definitely between 1 and 2. 6, 7. That's too big. 5/3. 5/4. 10/6, but that's the same as 5/3. We already got it. 15/12 is the same as 5/4. I think that's it. I think those are the only ones that we can get between 1 and 2. So let's test those, and we'll hope that one of those comes out. So second calc value, 3/2. Nope, that gave us 21. 5/3. Hey, eureka! We have found it. -1e -11. We know that means 0, right? In calculator language, that means 0. So we found it. We found our other one. Sweet. Okay, that's it. So we got 5/3. Now I'm not going to bother hunting down this fourth one because I know if one of my roots ends up being irrational, they always come in pairs. So there's going to be another one that's also irrational. So I should have 2 rational ones, 2 irrational ones. I've got my 2 rational ones. And I prefer to write this as 3x minus 5. You could call it x minus 5/3. That would work also. But I'd rather not have fractions. Any questions up to this point? So it sounds to me from talking to you guys last Friday, like you didn't have the luxury of using your calculator to do all this work last year. You had to hunt them down by hand the entire time, which is, you know, I've been there, I've done that too. It's not fun. We're going to use our technology this time around. All right, that means we still got 2 more irrational zeros to find. We're going to have to divide out the 2 factors that we know. And then probably use quadratic formula to find the last 2. Maybe not. Maybe we'll get lucky and it'll be something nice like x squared minus 3 or something like that. But we'll see how it goes. All right, so let's take our original coefficients. 12, negative 32, negative 61, positive 117, and positive 30. And let's use synthetic division to divide out. So we're dividing by, I'm going to divide by x plus 2 first. So when I divide by x plus 2, we're going to have a negative 2 in the box here. And we know that's a factor, so what should we get for a remainder? We should better get 0 for a remainder. So go ahead and do your synthetic division. And keep your fingers crossed for that 0. One, 2. Have faith. It's gonna work. It's gonna work. It's gonna work. It's gonna work. Yes, it's gonna work. So we didn't write this, or I said I wouldn't usually write this down, but I'm going to because this is our notes. What we have just done is we just factored out an x plus 2 from our original function. And we found a remaining factor of 12, that'd be constant x to the first, x to the second, x to the third. So 12x to the third minus 56x squared plus 51x plus 15. That is our function. If I were to multiply that out right now, I would get back to my original function, the thing that we started with. So we got another factor. Let's take this now and divide it by 3x minus 5. So we'll do that with synthetic division. So I need a little more space. I'm going to have to copy this down again. So this is the new factor that we created. We're going back to this now. We're starting from here. And we're dividing by 3x minus 5. So we need to figure out what's going to go in the box there. It should be the 0, 3x minus 5. So set it equal to 0 and solve. And I think you're going to get 5/3. Hey, can I give you guys a little shortcut here? Mental math shortcut. Some of you probably already know this. I know some of you definitely know this. This is going to make your life easier, so don't miss this. If you take 12 and multiply it by 5/3, you are essentially doing 2 different things to 12. You're multiplying it by 5 and you're dividing it by 3, but you can do those two things in any order that you would like. So make it easy on yourself and do the division first and the multiplication second. Mentally, when I do this in my head, what I think is 12 divided by 3 equals 4, and then I'll go 4 times 5 to get 20. It's easier to divide first usually because that makes the number smaller, right? And then you multiply to finish it off. Okay, so this way you don't have to use your calculator so much. So when I drop my 12 down, I got 12 times 5 over 3 is, I'll think 12 divided by the 3, and then whenever I get multiplied by 5, then that gives me 20. And I get negative 36. And again, negative 36 times 5/3, you'd think you might need a calculator for that, but I bet you don't. Do negative 36 divided by 3 first. That's negative 12 multiplied by 5. You get negative 60. Negative 9 divided by 3 is negative 3, times 5 is negative 15. And hey, we got a 0 here. All right, I need you to see this step here. You guys said that you divided by things with fractions last year. I need you to know that if we're dividing by something that has a coefficient, when we do synthetic division, we must divide by that coefficient after we're done. We're going to do one more step here. The coefficient was 3 here, so we have to divide each of these things by 3. So this is not actually correct. The correct would be whatever all that stuff is divided by 3. So we have now accomplished this. We've rewritten our function as the x plus 2 that we originally factored out. We just divided out a 3x plus 5, or sorry, 3x minus 5. And after doing so, we were left with this, which is 4x squared minus 12x minus 3. It does. So when you're doing that poly project, that part B, this is what you're doing, right? You start with the original, you do your division, make sure you're writing down both things. And then when you divide again, this carries down, but then the other two things come down. That's essentially, so you don't know the pieces, you just need to make sure you found them all in one thing. Okay, the question was, why did we have to divide by 3 here? Okay, so technically, whenever you do this synthetic division, you're dividing by x minus whatever's in the box. So we did not divide by this. We technically divided by x minus 5 over 3 when we did this. Okay, and we got this stuff. And this is all right. It's just we didn't actually divide by what we wanted to. Now, what's the difference between these two things? I'd say that this is just 3 times this, isn't it? If you multiplied everything here by 3, you would get this. Correct. So we divided by something, but we didn't quite divide by enough. We needed to divide by this and also another 3, and that would get us to equal this. That's the technical reason. Okay, the part that I remember is if I'm dividing by something with the coefficient, I just have to remember to divide by that coefficient as well. We could have kept these coefficients. I would prefer to have, so the question was, why didn't we write this as x minus 5/3 instead of 3x minus 5? I guess tradition. I'm used to, having done lots of upper level math stuff, you rarely see a factor that looks like this when it could be written like this instead. So, but they're both right. So if I had gone with x minus 5/3 here instead, then I would have used the original coefficients instead. Great question. If we do the quadratic, are we going to get the same thing? Answer is yes, right? Because if we went with the original coefficients, Actually, before I even did the quadratic formula, I would probably look at all those numbers and say, oh, they're all divisible by 3. Let's make it easy on ourselves when we do the quadratic formula and divide both sides by 3, which would get us the new coefficients anyways, right? What am I doing here? Yeah, it should be a 12. So either way, we're solving, that factor is going to end up being the same thing, whether it's this or 3 times that, should give us the same zeros. All right, all we got left to do is a quadratic formula question before we do.
Yeah. So then, in fact, you want us to do quadratic formula rather than like irrational zeros as like x minus.
We'll rate it out both ways. Okay. We'll rate it out both ways, and then it'll depend on the instructions which version they want. So we'll rate it out both ways, and we'll note how the instructions will be different for each. So stay tuned for an answer to that question. All right, go ahead and do your quadratic formula on that. As I've said a couple times in this class, if you are not comfortable doing something that's algebra 1 or early algebra 2 level stuff, we're not going to be spending time covering the quadratic formula in class for a third time this year, probably fourth, because you probably did it in geometry. Now you guys are coveted out of geometry, so you probably didn't do it in geometry. If you need some additional assistance with quadratic formula, let me know. We can hang out at lunch or before or after school, and I'll get you caught up on it. It's not hard. I'll tell you the answers you're looking for. Use this as an opportunity to practice. No. No, I spent like, the question was, did I do that in my head? No, I spent like half working it out. What do I call this? Irreducible. Actually, I told you a slight mistruth. I did work this out on paper, but I actually, when I created this problem, I started with these factors and multiplied them all together. I didn't do that in my head. I left Wolfram Alpha to do that for me. You ever heard of Wolfram Alpha before? Do all this stuff for you. second and I'll show you what I mean. So depending on the instructions, we're either going to write all of our factors out like this, including the irrational ones. Or if they ask for a product of linear and irreducible quadratic factors, basically they mean those ones that are going to end up giving you irrationals. Just write the original quadratic rather than splitting it up into the two. That's not super important for right now. That's going to show up in our homework for 3.5, which we're not even doing tonight. We're going to do that over the weekend. Tonight's homework's just practicing a bit more of this and then reviewing complex numbers, imaginary numbers. All right, now, so these problems are big and there's lots of moving parts. So we just took an entire piece of paper, at least for me, for some of you, it was probably 2 pieces to do one problem there. And there were a lot of different steps to it. So I want you to take a minute and just kind of look over the process. Like most things in this course, the process is relatively straightforward. It's all the details that you got to do to step through that process that where things get a little bit tricky. Okay, so take a minute, zoom out your focus, and look at this problem again from beginning to end, and just kind of walk yourself through what are the main ideas you did here. We use zeros to find factors. That's kind of the key thing, right? And we found zeros, as many as we could anyways, from the graph. Zeros are x-intercepts on the graph, if they're real. We found the zeros that we could using the graph. We used our P over Qs to help us find some of those that weren't so straightforward. Once we exhausted all of those, then only then did we fall back on synthetic division. This is a pretty tedious process, but look at this silver lining. At least we don't have to do it by hand without a calculator, right? Could you imagine if we had to do this entire problem by guessing and checking our way through this entire P over Q list? It would take forever. You might end up doing synthetic division 20 times for a single problem if that were the case. All right, ask some questions. Yes. Well, I'll show you. Here's my work. So did you end up with 12 plus or minus root 192 all over 8? So 192, I started playing around with it and I just started dividing it by stuff and I found that 64 did to go into 192. So 192 is 64 times 3. And I know what the square root of 64 is. So kind of the big step to answer your question is from right here to right here. Right, so the square root of 64 was 8. And then I don't know, we don't have a nice number for root 3, so it's just got to stay. So then that 8 ended up canceling with the 8 that was underneath it. I always, when I get to this step where I actually plug in numbers and I start simplifying, I always split it up into 2 fractions at this point. Otherwise, I'm prone to making a really common mistake, which is people will sometimes want to cancel the denominator with the first thing, but forget that it also is applying to the second thing. So to avoid that, when I get to this point, I'll always split it up into 2 fractions and then simplify them separately. Does that answer your question? I think I originally had 16 going into this, which it does, but then And I was like, maybe something bigger goes in. I saw the 8 on the bottom and I was like, well, I wonder if 8 goes into it. Okay, and I'm kind of being slightly dishonest because I actually knew what the answer was going to be before I started because I created the problem so it would specifically have this answer as our thing. But kind of pretending that I didn't know that, I probably would have looked at this 8 and been like, all right, let's see if we can get 8 squared to go into 192 so that we can cancel. And then if that didn't work, I'd try 4. See if 16 went in there. Yeah.
You want us to, so like, I did it first. Two. You want us to rationalize the number for roots always, or is that okay?
So you're saying your final answer was 3 plus or minus, would you have 2 root 3 all over 2? I'd say in this case, split it up into 2. I think the reason being, when you split it up like this, this is kind of a particular form where you're splitting it up into a rational part and an irrational part, which when we're dealing with complex numbers, that's how we do it. So I would say this is probably, just looking forward at what you might end up doing with this in the future, you're probably going to want to get in the habit of doing it this way. A decimal answer, if I ask for a decimal approximation of it only. Otherwise, assume I want an exact answer. No, if I were looking for a decimal approximation, then I'd want you to put this whole thing in your calculator. Like if I asked you for a decimal approximation for that 0, then I'd be interested in like 3/2 plus the square root of 3. I'd be looking for that, which you could have gotten from like way back here too. You could have typed this whole thing into your calculator and gotten that decimal answer. Fair warning, I won't. I'm probably not going to ask you for a decimal approximation. I'd like to see you be able to actually work it out. Now you start working it out, and if you're on a test and I can see that you've done this, right? You've shown this step right here, but you make a mistake somewhere along the lines and you don't get this, you know that you're going to get, most of the points for it there, right? The other thing you can do at the end is once we've got these are our 2 zeros, right? We can go back to our graph and we can check them. So you can check and see if you did all that work correctly, because I can go back to my graph right now, do second calc value, and type in 3/2 plus the square root of 3, and hit enter and hope I get 0 for what, right? Or something super, super close to 0. I got something super, super close to 0. That makes me feel good about my work. And then I could go back and type in the same thing with a minus instead, 3/2 minus square root 3, and hit enter. Oh, good. That makes me feel good. So let's say you're on a test and you do all the work and you go to check it and you're like, it doesn't work. Make me a note, write a little star, say, I know this isn't right. I must have made a mistake when I did the quadratic formula or something, right? To me, if I'm looking at 2 papers and one of them got the wrong answer and one of them's got the wrong answer with a note that says, I know this is the wrong answer, obviously one of those person is showing more knowledge than the other one, right? They both got it wrong, but this person at least knew how to check and see if it was wrong and communicate that they understood that. So I'm going to award that with points. All right, any last questions over this? Do you guys want to see the beauty of Wolfram Alpha? I'm sorry, go ahead.
I just had a question. So I know that you can also find, like, if like we're like having trouble like finding the answer, can't you also find the answer from the second trace 0?
Yes, that's a great question. Now it's going to be tricky to do on this graph because my graph is so vertical that when it asks me for that left bound and that right bound, I'm going to have a hard time actually keeping it on the screen. But yes, you can. So The question was, can't we approximate our zeros by using the second trace 0? So you could come up with a decimal approximation. It's just that the left bound and the right bound are going to be tricky. You see how like my left bound, I'm hitting left and it's jumping off completely off the screen. So let's see if this works. Yeah, and it did give me that decimal approximation. So now is that going to help you find this stuff? I guess it gives you something you could check it against once you get your final answer. Other questions? Do I need to charge my battery? These rechargeable ones, the color ones, they don't warn you as early that your battery is about to die as the ones with the batteries. Those of you guys who have the ones with the actual physical batteries in them, they will warn you for like a week before your battery dies. These ones you might get like, yeah, so make sure before your test, make sure you check them and charge them batteries up. You ready to see the beauty of Wolfram Alpha? Let me show you this. You're gonna love this. It's free, so I don't know if I have grades or email or anything up here. All right, share screen. This. All right, so it's Wolfram Alpha. Do a web search for Wolfram Alpha. It's wolframalpha.com. This is going to be your saving grace for college level math, folks. You want to write this down. This thing is awesome. It does stuff that I don't even understand. Like I don't know what all this stuff is, but I can take and type any polynomial I want in here. So let's just type in the one that we just did. Minus 32x. It's really interesting when you're doing book problems with this because did you see how it starts like predicting? It has the predictive text thing. This is stuff that other people have typed in. So when you start typing in one from your book, oftentimes you'll see because someone else that has the same textbook has used this website to check their work. Hopefully they're just checking their work and not cheating. But this is akin to like photo math, but like at a much higher level. So, you know, obviously it's a tool that you can use to help yourself, but it, you know, you can cheat with it, but you know, that's not helping you. So look, it graphed it. It gave us this nice graph. Can you guys see that all right? Let me see if I can zoom a little bit. And then it graphed it again with another weird axis. And then it's giving us these alternate forms. Check that out. That's exactly what we got refactored, isn't it? And then I don't know why this is helpful, but it did that for us too. There's our roots. Polynomial discriminant. I used to know what that means, but I don't know anymore. Domain and range. They'll tell you the derivative. This is calc, indefinite integral, local maxes. Look at all this stuff. I don't even know what this is trying to do here. Some kind of weird probability and convergence sums. And the step-by-step solution is probably something you got to pay for, I think. I don't know. Let's see. Oh, no, look. Mine does. Oh, look at that. It's teaser. GoPro now. Yeah, I don't pay for it, but use it for, or you know, do what you want. Use it for good, not evil. So notice in Wolfram Alpha they don't have that version with the x minus 5/3, right? Because this would be kind of the preferred way to write it. But anyways, Wolfram Alpha for the win. It's going to help you. So when I created this problem last period with my prep period, I typed in, this is what I typed in. I said I wanted some roots, some factors here, and then I created the 3 halves plus or minus square root 3. And then I ended up putting that 4 out there because without it, we ended up with a whole bunch of fractional coefficients. So, yeah. For square roots, you can do a half, or you can just type SQRT. Yeah. If you're going to do like a cube root, then you can just do caret parentheses. Make sure you put parentheses around the fractional exponent. All right, so that's awesome. Thank you guys for your attention there. Let me stop this and stop my recording.